Here I go. I'm gonna bring in Adam. Adam, how's it going, man? How you
Oh boy.
doing?
I think I'm doing pretty good. How are you doing?
Super stoked. I've already had a couple of espressos because it's super late. So
You couldn't tell.
Oh, I know, I know. You know what? I never know what the word non-energy is because I'm always full of energy. It's better than other things. Anyway, so what do
Absolutely.
you, yeah, yeah, for real. So what do you got for us? What are you gonna talk about?
So today I have a talk on complexity. Unlike some of the other talks we've seen today, which had a lot of very hands-on, detailed dives into code and sorts and things like that, I'm going to look at more of the theory and the ideas behind why our software gets complex in the first place and what we can do about it.
Oh, that sounds super awesome. I'll tell you what, I'm going to bring your slides in and then I'm going to disappear and you have it. So have a great time.
Thanks very much. And thanks to Geekle for having me. Before we get started, though, I just wanted to acknowledge the absolutely heroic efforts of the organizing team. I'm sure many people are saying something similar, but the very fact that this summit is running today is nothing short of a miracle. So thank you for all the amazing work that you've done in the face of what can only be described as unprecedented challenges. So now we're going to get on to something decidedly more boring. We're going to look at the job of a humble software engineer. But I think it's probably worth me introducing myself a little bit to try and convince you that I know what I'm talking about. So my name's Adam. Uh, I've been at Google for just about 10 years now. My day job is to build front-end infrastructure to support hundreds of internal applications and something on the order of a couple thousand engineers. In my spare time, I'm the company-wide lead on our code health practices. So it's my job to write documentation and consult with teams on how to improve the quality of their code bases. When I have even more spare time, I work on quality and testing, and I developed our current quality and testing orientation class. Over the last 8 years, I've taught something like 20,000 new hires how Google thinks about testing and automated testing in particular. And perhaps the most important fact is that I love my dogs, something that you can see as evidence right here. This is Tolly. She's great. So over the last 10 years, I've watched many projects emerge, develop, and die at Google. I've consulted with thousands of engineers about navigating Google's internal infrastructure, which, for lots of reasons, is just really complicated. Today, what I'm going to do is share some of the observations and lessons that I've learned. Now, I know it's a common trope to hear people from Google speak and then walk away thinking, "Well, my company doesn't have Google scale problems," and I get that. But in the case of complexity, while it may be true that we at Google have a lot more complexity, I'm going to be willing to bet that your teams have complexity too. So I want to start this talk with what I hope is an uncontroversial opinion, and that is that software engineering is complicated. But I think it's also worth asking what makes it so complex. So for starters, you have to keep all kinds of tooling and folklore in your head. There's all kinds of context you need to keep in mind every time you're making choices. Worse, all the information you're learning is completely arbitrary. That means the only way you can really learn it is to memorize it. I mean, yes, some things may be written down, but how much and what's out of date, who really knows, right? Fundamentally, the only way to become an effective team member is to make a ton of mistakes and ask a lot of questions. It's painful, it's inefficient, but it eventually works. Now, the funny thing is that if you ask a developer from 40 years ago why it was hard to ramp up on their project, they would probably give you a similar answer. The reason it's hard to be a software engineer is that software is complicated. Now, I know this is obvious, but I think it's worth stating. Software is complicated. So, what is complexity? We use that word all the time, but what do we actually mean when we say it? Well, I think of complexity as a feeling. It's a feeling you get when you're looking at a problem and you find yourself hesitating to act because you can't be sure what the consequences are. Complexity is experiential, which means it's also subjective. We are in the habit of saying this or that thing is complex, but of course, there is no absolute measure of complexity, at least not in a way that really captures what it feels like to be staring at a million lines of code for the first time. So, for this talk, I want to keep it simple. I'm going to define complexity as the amount of stuff that you need to keep track of to get your job done. Now, even the topic of complexity can itself be, well, complex. But I want to focus on a specific kind of complexity today. And to help us get there, I'm going to start with a taxonomy that was developed by Fred Brooks in his famous essay called No Silver Bullet. I'm sure you all have heard of this. In that essay, Brooks split the world of complexity into two important categories: essential and accidental. Essential complexity refers to the natural complexity of a problem. For example, when you're designing tax software, the local tax code represents the rules and processes that have to be followed. This is essential complexity. You typically can't get rid of essential complexity. And while essential complexity can be really interesting, in this talk, I'd actually like to focus on accidental complexity. Accidental complexity is the complexity that arises from our choices about how to solve a problem. Every time an engineer has to stop and work out why a library or service doesn't match their intuition, they are wrestling with accidental complexity. The problem is that all of our APIs, our libraries, our user interfaces, they're all littered with accidental complexity. It often feels like we barely have enough time to figure out what problem we're trying to solve, let alone the time to design concise and comprehensive solutions. Unfortunately, many of these quick solutions end up lasting for a very long time. You probably don't have to look too hard around your own code base to find some sort of quick and dirty hack that you've been working around for years. Now, most of us don't set out to build complex software, but more often than not, we end up there anyway. This is the nature of continuously solving problems based on incomplete or changing requirements. Over time, a series of locally optimal trade offs can make global problems, right? The end result is unsurprisingly incredible complexity. This is not a novel observation, by the way. The first time the problem of complexity was identified was back in 1968, and at the time it even had a name. It was called the software crisis. What was the software crisis? Well, according to Wikipedia, the software crisis was the recognition that, due to the rapid increase in computer power and the complexity of the problems that could be tackled, software systems were getting too big to understand. The effect was an epidemic of projects coming in late and over budget, if they finished at all. In fact, here's a quote from Dijkstra on the subject. The major cause of the software crisis is that machines have become several orders of magnitude more powerful. To put it quite bluntly, as long as there were no machines, programming was not a problem. When we had a few weak computers, programming became a mild problem. And now we have gigantic computers, programming has become an equally gigantic problem. And I need you to note the year on this. It is 1968. This was more than 60 years ago. The fastest computer at the time, the gigantic computer, was a Cray 7600, which boasted a whopping 3.8 megabytes of RAM, and it ran at a blazing 36 megahertz. Now, I know it's easy to laugh at that scale, but what this means is that less than 10 years after programming really got going, the smartest people in our industry were already worried that our systems had become too big to manage. Now, not coincidentally, this quote was captured at the same conference when the term software engineering became introduced to a large audience. So we had this problem in 1968. What did we do about it? Well, a lot actually. We started calling ourselves engineers, for example, right? And if you name us engineers, obviously we must be doing engineering. We of course then tried to act like it. We developed new techniques, things like structured programming and eventually object-oriented programming. We also invested in process development. We created things like waterfall, which I know it hasn't worn that well, but it was an attempt to solve a real problem. Now, all of this begs the question, what happened to the software crisis? For many of you, this is probably the first time you're hearing about it. The unsatisfying answer is that after 20 years, people sort of forgot about it. Seriously, I mean, I spent weeks hunting around on the web trying to find an explanation of what happened to the crisis, but I couldn't find anything. And as it turns out, we're still able to build a ton of useful things, even if we aren't quite sure how they work. So, if we solve the complexity crisis in the 80s, why are we talking about it again? Well, it's because the complexity never actually went away. In fact, we've been quite busy making the world much more complex. For example, our systems have grown by orders of magnitude. Our architectures are more complex. At least with a monolith, we could locate all the complexity in a single binary. Now, microservices have traded local memory and concurrency problems for globally distributed ones. Those changing architectures have allowed our teams to grow faster, though. And the scale of our teams has allowed us to move faster overall. And I don't know about you, but I'm not turning down near as many systems as I'm building, right? That means all of this stuff is just piling up. But perhaps the most important change, we solved the software reuse problem, right? When I was in college, which wasn't that long ago, software reuse was often described as a good idea that just never worked out in practice. There was no way to get all these cool libraries shuttled around the earth. Well, it turns out that it really was just a distribution problem. And the advent of the internet made it really easy to share libraries. And it made it so easy, in fact, we fully automated the process. Today, you can pretty easily find a library that does almost anything you want, and with a couple command lines, automatically add it to your project. And you'll get complete and continuous updates forever. Now, I want to be clear. This talk is not coming out against reuse. I think reuse is great, but indiscriminate reuse amplifies project complexity faster than you can grapple with it, right? All of the systems that you're running today depend on millions and millions of lines of code that you're never going to see. So the TLDR and complexity in 2022 is that we have more software running in more places, changing faster than ever before. The world has just gotten a lot more complicated, and it's more than just technical complexity. My guess is that the amount of code that a single person can create probably hasn't changed so much in the last 50 years. But the fact that our teams are getting larger and more distributed and moving faster has created much more for us to keep track of in order to get our jobs done. And personally, I think we're overdue in developing a few new ideas and maybe maturing our practices a little bit to keep up. So before I tell you what I think will help, I want to reframe the problem a little bit, right? I'm going to make the case that software complexity is actually a user experience problem. And I like this framing because it allows me to start applying UX solutions, which, I'm a front end engineer, so this is how I think about the world. Specifically, I like to think of complexity as a human factors problem. Now, for those who haven't heard the term before, human factors is the study of how to reduce human error, increase productivity, and enhance safety. It's basically all the things I want for my project. But if we're going to get into the human factors of our projects, we need to investigate where the problem starts and understand a little bit about how humans process information. So let's start by recognizing that software is purely abstract. That means it really only exists in our minds. Yes, some of our software involves physical systems, and yes, we do write code down. But the conceptual organization embedded in our code, the objects, the relationships, they're entirely abstract. The meaning is what we take from it in our minds. Take the humble service class. What properties does a service have? What behaviors can it perform? Who knows? Service is a perfectly abstract and frankly meaningless noun. It means whatever we decide it means in our code. When you and I develop software with abstractions like this, we often have to implicitly fill in the blanks about what kinds of behavior these objects should have. Now, there are other disciplines that are entirely abstract, mathematics, for example, but whereas math is filled with deep abstractions, it's also built on an equally deep set of rules and definitions. By contrast, software obeys almost no generalized rules beyond the type system and language semantics. All of the interesting organizational aspects of software are completely arbitrary. I bet you could grab the definitions of 5-person classes from 5 different systems and they would each be different. That's what I mean by arbitrary. Every time we develop a system, we have to recreate all the definitions and all the relationships from scratch. Now, in practice, we eventually stumble our way to agreement on what each abstraction will do, but it never seems to get easier. So if you really want to tackle complexity, then you need to grapple with how humans process information that is both abstract and arbitrary. Information processing, I'll be honest, it's a very deep field, but for our purposes, there are 3 simple concepts we're going to look at that will help orient us a little bit. The first is cognitive load, the second is chunking, and the third is multimodal instruction. So let's start with cognitive load. Cognitive load is a measure of the amount of working memory required to perform a specific task. That's a fancy way to say, how many bits of information do you need to keep in your head to get something done? On a software project, the bits of information look like your manual deployment process, all the steps involved, or a set of weird command line flags you have to remember. The rub is that there's actually a limit to how many things someone can hold in their mind before they start forgetting. Studies consistently show that when we create cognitive overload, it leads to mistakes. Unfortunately, engineers are really good at creating new cognitive load. Next, chunking. Chunking is a process by which individual pieces of information are grouped together into meaningful chunks. Chunking is why, when you give someone your phone number in the US, for example, you say something like 303 515 8764 and not 303 515 8764. It's also the mechanism at work when we develop mnemonic devices that help us to remember a long list of shopping items, for example. Chunking allows us to hold a smaller number of items with more content in them, right? It helps us keep that in working memory, which then helps us bypass our limited capacity and thus reduces cognitive load. In fact, I wouldn't be surprised if it's our affinity for chunking that explains why techniques like object-oriented programming and encapsulation are so appealing to us. Both of these ideas allow us to chunk parts of our system into information-dense shorthand. The last information processing concept I want to cover is called multimodal instruction. Now, I'm sure at some point in your career, you have encountered the idea of learning styles. Learning styles are the idea that some of us learn better by reading or working with our hands. Well, as it turns out, most of the ideas about learning styles don't hold up empirically. But one idea that does seem to matter is that all people retain information better when they encounter it in different mediums. That means you're more likely to retain information if you read it and see a diagram to go along with it. Okay, so to quickly restate, the three concepts to be thinking about as I go through the next slides are cognitive load, or how much space you have in working memory, chunking, the idea that you can manage more information when it's grouped together meaningfully, and multimodal instruction, the practice of using multiple ways of communicating an idea. All right, now we know a bit more about how humans process information, we can talk about how to apply it to human factors in developer experience. Now, what I'm going to share is not intended to be an exhaustive list, but rather just a set of observations that I've made helping teams at Google for the last 10 years. I want to look at four distinct ideas. The first is something I call complexity gardening, and then information management, followed by system modeling, and finally, I'm going to look at what happens when we give up and just embrace complexity. Many of the ideas I'm going to share will seem like common sense. Others are a little more out there. But even if you're familiar with these ideas, I think it's important to consider them in the context of managing complexity. So let's get started. Complexity gardening. Complexity gardening describes the set of small, often tactical choices you can make every day to keep your project neat and tidy. Complexity gardening covers a lot of the easy to adopt good habits you probably already know. And frankly, I just wanted to take the opportunity to remind you to keep up the good work. The easiest way to start with complexity gardening is by being an advocate. As engineers, we are continuously making choices about a wide range of problems. Some small, like whether or not to add yet another conditional, or some much larger, like how should we build our deployment pipeline? When you and your team are doing code reviews or making technical decisions, ensure that someone is making the argument for simplicity. Don't be shy about saying you ain't going to need it or yagni, because in a lot of cases, you won't. Now, advocacy within the team is a good start, but it's all for naught if you can't convince the product owners to embrace simplicity as well. In my experience, some simple back pressure on requests from product managers can really work wonders. As a professional engineer, you should feel very comfortable asking your PMs and your managers why they're giving you unreasonable requests or confusing guidance. Don't just accept change for change's sake. Ask, why are we changing directions? Why this feature set and not something else? If you're not hearing a good answer from the people who are in charge of giving you that answer, you should stop as a team and discuss. Now, a little goes a long way when it comes to pushback, so please be polite and focus on the big sources of pain initially. If you do a good job managing your relationships, then over time you can grow into a more sophisticated set of discussions around product complexity and sustainability overall. The next set of recommendations are focused on how you manage your code base. And perhaps the best advice I can give you is look around. Before you start developing code to solve a problem, look around and see if code really is the best solution. If code is the best solution, look again and make sure no one else has already solved the problem by writing a library or building a service. A little looking may save you a lot of implementation time. And more importantly, it will reduce duplication. You don't need two UI testing tools. One is enough. In my experience, the best time to address complexity is before you create it. So look first and then take action. Now, of course, you will eventually have to write code, and when you do, you need to make sure you're practicing relentless refactoring. I hope you all know what refactoring is. It's the act of changing how the code does the job without changing the public behavior in the contract. Refactoring is a key practice for keeping your code base clean. You need to refactor to clean up ideas that don't quite work. You need to refactor to make things more consistent. You need to think of refactoring as a garbage collector. It catches complexity before it can impact you. And like garbage collection, it's best practiced continuously rather than triggering some sort of stop the world pause in your development process. Now, a quick word of warning. Refactoring has to be a team sport. I've seen too many teams with a single refactoring champion. They just can't keep up with the volume of work produced by even 4 other engineers. Refactoring has to be treated as a part of the day-to-day work of the entire team. The last bit of active complexity gardening I want to recommend is pruning oddballs. Well, what's an oddball? They come in a lot of shapes, but as an example, I want you to imagine a series of 5 event handling functions, 4 of which are named with the prefix process event, and the 5th inexplicably begins handle event. The thing is that our brains are exceptionally good at detecting patterns and generalizing from them. And likewise, we are easily triggered by pattern violations. When we encounter an oddball, there's a great deal of quick mental processing that we engage to figure out, why is this thing different? Why handle and not process? What was the author trying to tell us? We're often left guessing if there was a subtle meaning or if it was just a lapse in consistency, but we can't really know. Oddballs increase our cognitive load, and that increases the chances we will make a mistake. So if you see an oddball, get rid of it. Now, the corollary to this is that you should also try really hard to follow local customs, and that includes for things like formatting and naming. Don't go around creating oddballs just because you like tabs better than spaces. That would make you a monster. In all seriousness, though, I know that each bit of duplication or oddball may have made sense at the time, but over the life of a project, the accumulated cost of having to keep track of so many inconsistencies makes it really difficult to reason about the health of the project. That brings us to persist. Persist is the last and maybe most difficult topic when it comes to complexity gardening. Persistence in complexity gardening is really about ensuring your efforts are sustainable over time. One strategy I found that works really well for keeping projects sustainable is to make your managers happy. And you know what? Managers love quantification. Now, I know that quantifying the impact of removing complexity can be a fuzzy proposition, could be downright impossible. However, I still encourage you to try to set meaningful goals for yourself. My advice is to start with user journey level metrics, things like how long does it take for a new person to contribute their first production code? Keeping your metrics high level and outcome focused allows you to be creative in how you address them, right? A lot of engineers at Google, and I've talked to a lot of engineers, they've told me that their managers don't support decomplexifying work. So I got to be honest, it came as a bit of a surprise when I went and talked to those same managers, because what they told me is that actually they're really supportive of fixing complexity, but they feel like their tech leads often fail to provide meaningful business justifications for the change. Here's an example of a problem that I've heard. Say for example, you want to reduce the number of command line flags in your app. You might say something like, hey manager, I'd really like to reduce the number of command line flags. There's just too many options. Well, that's not a very compelling justification for someone who's got to make business decisions. Instead, you should say something like, I want to capture X% of lost revenue by reducing production outages, 40% of which are caused by the confusion in the use of configuration flags. Now, I know it's a lot more words, but the point is you're tying the work you want to do to some meaningful business goal. And make no mistake about it, decomplexifying your apps does meet business goals. It's your job as a tech lead or as an engineer on the team to connect the dots for your manager. In other words, help your bosses help you. Learn to speak their language. The next thing I want to do is encourage you to finish your migrations. Migrations are some of the most complex projects we undertake. They take a long time, they involve all kinds of duplication, duct tape, they come with dubious deadlines. They are the perfect breeding ground for complexity, a lot of which will stick around well after the migration is over. And all of this gets exponentially more complex when you have more than one migration going on at the same time. If there's one lesson I've learned at Google over and over again, it's this: don't start a migration unless you can finish it. And once you do start, do not stop until you are done. So fundamentally, a lot of the ideas about complexity gardening can be summed up as consider the total cost of ownership. The total cost of ownership just means you need to consider the lifetime costs of your technical choices. After all, the initial implementation costs are always dwarfed by the ongoing costs of maintenance. When you're making technical decisions, take time to consider the process costs, the deployment costs, the support costs, whatever. If building a new service or adopting a new framework makes your life even a little bit more complicated, consider how that decision will age over the next 5 years. And to complete the metaphor, a garden is never done. As long as the plants are alive, they will need tending. And so it is with your code base. The accumulation of technical debt, migrations, and other debris will never stop. So you're going to need to invest continuous low level effort to keep the introduction of complexity at bay. Okay, let's move on to information management. Now, despite all the effort we put into organizing our information for our customers, we often do a comparably poor job in organizing information about our projects. This is weird to me because we're kind of awash in information, right? Our projects are throwing off information all the time. Unfortunately, a lot of that information isn't very high quality, and even if it is, it can be hard to find. So I want to take a look at some things you can do to reduce the complexity in the information around your project and maybe even increase its value. First, I want to just quickly remind us that there is value to documentation and stored information, right? Written docs have great scaling properties. Believe it or not, we've actually built a great interconnected network of computers for distributing sets of linked documents. We should probably use it. Better still, if your teammates are documenting their decisions, their designs, and strategies, the team won't collapse when they win the lottery and take off. Documentation can be read at any time. It can be marked up, reacted to, disagreed with, all without the creator being involved. It's also more inclusive. Putting information in documents allows people to consume on their own schedule and in their own way. In many cases, it allows people to collect their thoughts and develop better responses. That is, assuming you do not have a team full of trolls. The bottom line is the information that your team creates has a lot of potential. So step one in managing that is writing it down somewhere. Now, I'm sure I didn't need to convince you that writing documentation was a good idea, and that's fair enough. But that begs another important question. How do you decide what to write? Well, I say err on the side of writing more down in general. Obviously, this includes artifacts like design documents and product requirements, but it also includes anything that's necessary to be a productive developer on the team, like how to get onboarded, how to run your application locally, how to respond to an incident. All of this stuff needs to be written down. One really nice technique that I found useful at Google is to write down a decision log. A decision log is just a list of all the decisions the team has made and why. Uh, Having a decision log allows the team to track its sort of evolution over time. This helps new teammates understand how we got where we were or where we are, and it keeps the rest of us honest so that when we end up in a mess, we know how it happened. Right? Decision logs are fantastically valuable at settling arguments that keep coming up over and over again. Basically, what I'm saying is you need to get your team's lore, all the stuff that's in your collective consciousness, you need to get that written to persistent storage somewhere. So I know I'm advocating for a lot more documentation, and I have to be honest that in my experience, most engineers have not been trained to write very well. That includes me. I would consider myself a writer in training. Writing good docs that communicate clearly takes a lot of practice. So you need to encourage your team to write a lot. Maybe you should encourage everyone to take some writing classes, yourself included. It can't hurt. Make documentation everyone's responsibility and reward major documentation achievements just like feature achievements. And once you get your team to start generating docs, you have to remember that they can live a long time. Make sure that your documents and diagrams are version controlled. Even better, if you can annotate why things change over time, you can add that to your decision log. Of course, once you start creating a bunch of good docs, you'll also start making some obsolete. Make sure to keep things updated and purge them entirely. I'm sure we can all agree that the only thing worse than no documentation is documentation that is out of date. Now, if you're successful at getting your team to write everything down and write it well, you'll have a new problem, which is finding stuff. Documentation is only useful if you can find it when you need it, so it pays great dividends to think about how people find information on your project. The costs here are not theoretical. In my experience, junior engineers are especially uncomfortable asking for help and would rather spend days hunting around on a wiki than talk to someone on their team. And I don't think this is good, but I see it all the time. So I think you need to plan for this reality. You can start by doing a study of the user journey of a new engineer learning your system. Where do they look for information? How easily are they able to understand what docs are written down? What do they do if they can't find an answer? A great North Star for your docs is that a new hire can get reliably productive without having to ask anyone on the team questions. Remember, they might not feel comfortable doing so. Now, again, I want to stress, I don't think it's good for new hires not to talk to people. But in my experience, it does seem to be the case they don't. So you should have enough good docs that they can get their job done in case they are a little shy. I also think it's a good idea to task new teammates with fixing up the team docs or the wiki or whatever. It gets them involved and it empowers them to take ownership of the experience. Next, you need to think about where that information shows up in context. If you can, put important information where it's most helpful. Whether that's in help text in a tool or inline in a playbook, it doesn't matter. Don't make people hunt down something that if or memorize a bunch of breadcrumbs or whatever. If you could provide what they needed in a simple inline link. Now, last, you need to think about how you can guide people through the process of learning about your system. Learning is a multi-step process, so consider writing docs at multiple levels of abstraction to help people build chunked representations of your system. Try to keep in mind that multimodal information, pictures and words, help people develop mental models faster. So be creative in how you capture the important details of your system. And if you're lucky enough to have access to one, talk with a tech writer. They can usually help you organize the information about your project into a useful taxonomy, which makes it easier to find things later. Oh, and one more thing. Because I'm from Google, I'm obligated to say, get a good internal search engine. Look, information is gold on most projects. The least we can do is show it a little respect. Now we're going to shift a little bit. We're going to talk about some ideas that are a little more theoretical and a little more abstract. We're going to talk first about how to model your system. Now, what's a model in this context? Well, it's really any artifact or aid that you use to think about how a system will behave. Most models attempt to simplify major parts of a system so you can focus on the interesting stuff. This is chunking at work, and it's what allows us to communicate about complex problems in much higher bandwidth. Believe it or not, you're making models every time you name an object, write a design doc, or draw a diagram on a whiteboard. Models are crucial because they are often the only tools we have to orient ourselves or communicate about our systems. Now let's get a little more precise about the job of a model. Roughly speaking, a model's job is to help us build an understanding of a complex system so that we can make predictions about how it will behave. The quality of a model can be judged by how well it helps us make decisions about the future. A good model helps us develop reliable intuitions about how real systems work, and that helps us make decisions about how potential changes will impact that system and do so without having to run the whole thing, right? If we can look at a model and understand what's going to happen, we don't have to, deploy code out to the production environment. Unfortunately, building good models is actually really hard. Now, to prove this to yourself as an exercise, when you get back to your team, ask everyone to draw an architecture diagram of your system. See how many different shapes you get. I'd bet good money that despite all of you working on the same systems every day, no two diagrams are going to be identical. And that's not necessarily a good thing. But I also don't think it's your fault. Our industry, other than the folks in the domain-driven design crowd, don't add me, y'all. We haven't done a great job of centering the need for better modeling. And the problem with that is if you and your team aren't working from the same models, you may not share a consistent idea about how things work. And a lack of consistent understanding among the team leads to weird and inconsistent design, which of course ratchets up complexity over time. Spending a little effort to get your models right can save you a lot of pain. Now, as great as models can be, it's also important to keep in mind that they have inherent limitations. Perhaps all of you have heard the quote, all models are wrong and some are useful. Well, it's true, all models are wrong to one degree or another. That's because they are, by definition, abstractions of the underlying reality. They are not reality. For example, when you are when you are talking through the user sign-in flow of your web service, how much time do you spend thinking about data corruption? Data corruption can certainly impact the user sign-in flow, but in most circumstances, it's not an interesting detail to the problem you are trying to solve. Does this mean that your wireframes are a bad model? No, of course not. What makes a model useful, despite being incomplete, is that it includes the relevant details at the right level of abstraction for the problem at hand. The worst outcomes I see when it comes to modeling often come down to a fallacy known as the map territory problem. The map territory problem is simply a reminder that a map is not the territory. More generally, don't confuse a model of reality with reality itself. Remember that all models are missing information of one kind or another, so you need to regularly check and make sure your models are aligned with reality. The corollary to this is that as your system evolves, the models need to change too, and this may include renaming objects, evolving system metaphors, and updating architecture diagrams. Don't let your best communication tools get stale. All right, so that's enough about what models are and how they go wrong. What makes a good one? I think a good model starts with good names. In software systems, we have to name everything. Everything we build and interact with needs a name. And often we have to come up with those names on the fly. The names we give the nouns and verbs in our systems are incredibly powerful, and they form the kernels of the models we will build. Names shape our implicit understanding of the abstractions we are working with. They are a chunked way of communicating what a thing does or how it does it. We do it so often, though, that it's easy to take for granted that the name of a thing is consonant with what it does. But in practice, we have to choose to enforce that requirement as we evolve the system. As classes and interfaces get larger, it can be much harder to maintain the discipline of keeping your nouns and verbs coherent. As you practice naming things, there is one thing I want you to be mindful of, and that is the implied cultural context. At Google, we used to be absolutely in love with clever code names for all of our projects. We name things after various movies and comic book characters, gods and goddesses, whatever, on and on and on. The thing is that none of these names conveyed anything useful about a system unless you had the specific cultural context that gave the name meaning. In other words, naming things based on your nostalgia for your teenage experience is a bad strategy. And more than that, it's exclusionary to those who did not grow up like you did. My advice is boring, and that is to name objects by what they do. Boring names do the job they are supposed to, and they do so without adding to the additional complexity. I know naming things is famously one of the two hardest problems in computer science, and the more I study it, the more I agree. But it's also something worth spending a little more time on to get right. So once you have good names, you can start thinking about the metaphor for your system. The concept of a system metaphor was one of the original practices of extreme programming, but weirdly, I don't hear it discussed all that often. Kent Beck defines the idea of a system metaphor as a story that everyone, customers, programmers, and managers, can tell about how the system works. Having a model of a system shared by every stakeholder is really powerful. It allows all parties to communicate efficiently in the jargon of the application. It also helps shape everyone's intuition about what the system can and can't do and how it should behave. Now, if a system metaphor is a story about what the system does, then growing and shaping that metaphor is kind of like building a small little world in which that story exists. The idea of world building is common in things like movies and novels. It's the process of creating an imaginary world that is really detailed and, importantly, internally consistent. World builders know an important fact about metaphor and story, and that's that little inconsistencies break the illusion and add to the cognitive load as you try to figure out why. So when you develop your systems metaphor, act like a world builder and sweat the details. Try to get rid of the inconsistencies. The more internally coherent your metaphor is, the lower the cognitive load and the less accidental complexity you're probably creating. And to be clear, I'm not advocating for modeling all your abstractions up front. I'm not a big upfront design guy. But I am suggesting that paying attention to how people on your team think, diagram, and communicate about your system tells you a lot about how strong your models are. If you notice frequent confusion or misunderstandings, consider investing in more modeling as a way to get everyone on the same page. Okay, last subject, embracing complexity. What happens if it all goes wrong? So, up until now, all the suggestions I've made are pretty actionable, and some may even seem just like a retread of good practices, and that's good, right? I hope you're doing a lot of them. But this last set of ideas is a lot more theoretical. I felt like it was important to include them because I got hit by them really hard last year. So I remember this. I remember a moment last year quite vividly. I was reading an internal postmortem about a flagship Google product that experienced a meaningful outage. And at our scale, incidents like this happen all the time. But this postmortem really surprised me. And surprised me because the team that built the service that went down did everything right up front. Everything. They did capacity planning, they followed the SRE. I mean, they did it all, right? We know how to do this. However, an improbable series of events coupled with multiple complex failures led to a cascading outage. The level of complexity that had to be documented in the postmortem was truly exceptional, and it actually changed my outlook on complexity substantially. I convinced myself that even some of our most simple systems are in fact so complex and so interdependent that we are never going to be able to reason about them reliably. In other words, our complexity may have reached escape velocity. Now, look, I know this sounds weird, especially after the last 15 minutes of me going on and on about all the things you can do to attack complexity. And believe me, I'm not happy to be saying this. I debated whether or not I should include it in the talk. But I really, and I got to be clear, I really do believe all the things I said before. I think they will help you. But if you need to understand the total behavior of your system, you can't do it by looking at design docs, test cases, or really any other model or representation. To really understand your system, there's only one option. You have to run it and see how it responds in its environment. The real running system is the only thing that contains all the potential behaviors, all of the complexity. Unfortunately, most of us cannot run our entire system with all of its dependencies anywhere outside our production environment, and that makes it risky to mess around with. Personally, I think we should ask more of our development environments. If it was up to me, I'd want to work on a system that encouraged me to poke at it and prod it. I want a multimodal environment that abstracts away the complexity, or at least doesn't require me to mentally account for it like some sort of meat space Turing machine. In 2012, former Apple designer Brett Victor gave this awesome talk called Inventing on Principle. I highly encourage you to go and find it. In that talk, he said, to a large extent, the people we consider to be skilled software engineers are just those people who are really good at simulating what the computer will do in their head. Now, when I watched this talk 10 years ago, this line just went right past me. But now I think I'm finally coming to terms with the implications. As software engineers, we build systems to manage and shape the complexity for all kinds of professional industries. But notably, we don't seem to apply the same power to our own work. As a result, despite the fact that the complexity of our systems has grown by orders of magnitude, we are still using a lot of tooling and techniques that have been common for more than 3 decades. Instead of using computers to make our jobs easier, we just keep asking ourselves and our colleagues to do a better job of pretending to be one. And in case it wasn't clear, that doesn't scale so well. So here's a question. What would your job look like if you could apply more computational power to the job of software engineering? So before we get into that, and I have some ideas, I want to take a minute to explore why we seem stuck where we are. In many other engineering disciplines, when someone wants to know how a complex system will behave in various conditions, they'll use high-powered software to model the outcome. For example, aerospace engineers working on a new airplane design can develop a working model in SolidWorks and simulate various physical stresses on the design. SolidWorks is a proprietary software package for doing engineering work. The key is that SolidWorks operates on a model of an airplane. It doesn't need all the details, like what color the seats will be. The system can make a lot of simplifying assumptions and still produce data that is very predictive of real-world outcomes. Imagine having something like SolidWorks, but for software. This is a tool that could ingest your code base and your deployment architecture, and then let you interactively simulate traffic, failure rates, tweak the bandwidth or memory, whatever. Further, imagine if this tool could generate a useful visual diagram of your system and begin highlighting when individual components exceeded their SLOs. Then imagine you could run the clock forward and backward. You could just mess with time to replay everything with slightly different values. The immediacy of a system like this would create an entirely new relationship for us and our designs. Unfortunately, there are some good reasons why SolidWorks for software doesn't exist. All physical systems have one thing in common, and that is a basic set of ground rules that we call physics. If you develop a program that understands basic physics and you throw in a bunch of horsepower, you can simulate a lot of complex phenomena. Having a set of hard rules allows you to make decisions about what you can simplify out of a simulation and ensure that your simplified models have predictive power. Unfortunately, software has no such rules. The closest thing we have to a rule book are the metaphors and mental models we develop, but those are both informal and, as we've talked about, we have to reinvent them every time we build a new system. As a consequence of having no fundamental law of software, it's really hard to build general simulation environments. Software is so much more complex than most physical systems we build. Even a modestly large software system will have a million lines of code and depend on millions more. What are all the potential behaviors in a system like that? Which ones can you simplify and still retain predictive qualities? What are the fundamental building blocks of a system like this? Which of those can be shared between simulations of different software systems? This kind of complexity means that every team and every project needs to build their own bespoke simulation environment. The reality is it's just a lot cheaper to hire a team of manual testers and hammer away at the application in prod and see what happens. And that's what we do. Software is just unbelievably complex, and that complexity is hard to model. Without good modeling, it will be difficult to develop general purpose simulators. So I regret to inform you we're not likely to see SolidWorks for software anytime soon. I don't want to leave you on a downer note though. While complete simulation might not be achievable, I think it may be possible to narrow the requirements a bit and land on something almost as good using virtualization. What would a robust virtualization developer environment look like? Well, first, we need a way to run our full system locally in some sort of hermetic container. And I mean everything, your code, your dependencies code, everything. Next, I want to add in direct manipulation of program state with live feedback so that when the runtime behavior changes, you get immediate response in state changes. This is actually something that Brett Victor explored in that talk I mentioned earlier. He's got a great demo of it. Next, we need to be able to control time. You should be able to scrub the CPU execution forward and backward. You should also be able to change the clock speed at will. You want to speed computations up or slow them down, you should be able to. Directly manipulating time can provide such visceral insight into how a system behaves, or more importantly, why it fails. Think about being able to step right to the point where you see a deadlock happen and then rewind to see why. Once you have time under control, then you'll probably want state transparency so you can keep track of what's going on. And I don't just mean like you can, set a watch on a variable. I think that it should be trivial to inspect any part of the running system anywhere and see what data is in memory, what past computations have been made, and what might happen in the future. If you get all of this, you're going to need something better than our current debuggers to make sense of it all. You will need a powerful visualization engine that can help you identify and isolate important points of execution in your system. That engine should be able to show you your architecture and your design in motion. And as you make changes, the visualization should update accordingly. It should be trivial to connect your single virtualized system to other dependencies in your code base, right? Because your code doesn't live in a vacuum. It's probably deeply interconnected. But you want to connect all the pieces together and see how they work. Imagine being able to trace a request from front to back while watching various side effects throughout the system. You'll be able to see the impact of unintended request fanout or potentially even request thread deadlock. You could even virtualize common types of cascading failure by reducing capacity of downstream dependencies or causing traffic overload. With a completely virtualized developer environment, you would have an interactive visual representation of your system. You would also be able to study the impact of a wide range of changes without deploying a single line of code. A tool like this would allow you to effectively do an end run around complexity. As cool as all of that sounds, we aren't quite ready for this future. Our languages and runtimes, our tool chains, they're just not ready for this kind of virtualization. We probably don't have the design patterns or techniques to support the required isolation from our environments. It's possible we will need new kinds of programmatic building blocks to enable some of the most interesting features. However, there are pieces of a solution floating out there in the world. We have tools like Kubernetes, which give us computation isolation. Virtualization itself is pretty well understood. In fact, there's even a great feature in VirtualBox. I think they turned it off, but it was called Warp Drive. It actually allowed you to change the speed of the CPU. Elm has a time traveling debugger. Observability, as we've heard throughout this conference, it's all the rage for production systems. These are all components of what this future virtualized dev environment might look like. The future may be a ways off, but one thing you can do today is start thinking about how you can create a more interactive development experience for your team. Make sure your local dev workflows are fast and your edit refresh times are short. Explore ways of visualizing your application state. The more tactile you can make your dev experience, the stronger models your team will build. And with stronger models comes stronger intuition. better design, and more manageable complexity. Now I'm almost done. I know my time is, I'm right at the limit here. So I've got 1.5 more slides. I know that was a lot to take in. And to be honest, there's so much more we could have looked at. We could have looked at how team size affects cognitive load. What is a team's collective cognitive load? I don't even know. How are processes like Scrum and Kanban interacting with complexity in our systems? How do we design the right incentives to reduce complexity? How does internal system complexity affect our users? I don't know. I also need to be clear that nothing in this talk was intended to tell you you're doing everything wrong and you need to rethink how you're doing your job. Nothing in this talk should be taken as a substitute for good engineering hygiene, including robust automated testing and talking to people and all the other things you're seeing here, right? I mostly want to get you to think about the future that we could live in. It's possible that if you're working on a small project or maybe a short-lived project, some of these ideas don't apply to you, and that's okay. I just want you to keep in mind that as your projects or teams grow in size, the number of things you're going to have to keep track of will too. Hopefully, using some of the ideas I talked about today, you can play an active role in keeping that growth manageable. Look, complexity is hard, and the accelerating pace of technological growth means it isn't going to get easier. Unfortunately, the way we're developing software right now isn't helping our minds keep up. I'm sure you've all joked at one point or another about how all the systems that you work on eventually become a big ball of mud. And the more I study the impact of complexity, the easier it is to see why that happens. So if I can leave you with one simple idea when you get back to your teams, it's this. Keep the human mind in mind when you build software. Exploit the human tendency to explore, to tinker, right? Make your systems tinker friendly. We are at the earliest days of software engineering, right? It's only been 70 years since all of this got started, but I think we're also at an important inflection point. The integral nature of technology in all of our lives has created a perfect storm of dependency, scale, and uncertainty. Complexity is never going to go away, but as professional software engineers, it's our responsibility to seek out better tools and techniques that will allow us to make better sense of our creations and their impact on the world. Thank you very much. I yield my time.
That was so super awesome. I really appreciate that, Adam.
You're very welcome.
Wow, I just got so many questions, but I gotta let you go for a few minutes.
We'll see you in a little bit.
See you in a little bit. Hey, go take a break, man. Have a cappuccino or something.
Yeah, I need some water. That was a lot of talking.
I was like, is the dude gonna take a break or what?
No way. All right, we'll see you in a little bit. Thank you.
Yeah, see you in a bit, Adam. That was awesome. I really appreciate it.